For generations, humanity has gazed at the night sky, charting the familiar path of our singular moon. Yet, in the vastness just beyond our immediate vision, an anomaly began to emerge. Early gravitational mapping data, primarily from the Kepler Observatory's exoplanet transit studies, hinted at a subtle, persistent perturbation within Earth's orbital system. This wasn't the expected influence of known celestial bodies, it was something novel, a faint echo in the cosmic dance that, initially, many dismissed as instrument noise or computational error. The whisper of something unseen had begun. How could such a significant celestial body remain undetected for so long? Researchers from the International Astronomical Union suggest several contributing factors. First, its orbit is highly eccentric and inclined, keeping it largely outside the common observational plane of Earth's primary moon. Second, its composition appears to possess an exceptionally low albedo, meaning it reflects very little sunlight, rendering it incredibly dim against the black backdrop of space. This combination created a veritable blind spot, obscuring its presence from even the most powerful telescopes. It was Dr. Eris Thorne, a theoretical astrophysicist at the SETI Institute, who first publicly championed the idea of a hidden lunar companion. In a controversial paper published in 2012, Thorne argued that the cumulative gravitational discrepancies observed over decades pointed unequivocally towards an uncatalogued mass. The numbers simply did not add up, Dr. Thorne stated in a subsequent interview. While the evidence was circumstantial, the persistent, unexplained perturbation in Earth's Lagrange points suggested a non-trivial celestial body exerting influence. His hypothesis, initially met with considerable skepticism, provided the impetus for a focused investigation. The initial evidence for this hidden moon was indirect, stemming from the meticulous analysis of existing satellite trajectories. According to a 2015 report by NASA's Jet Propulsion Laboratory, certain long-duration probes, like the Stereo spacecraft, exhibited minute, yet consistent, deviations from their predicted paths. These deviations, while minuscule on an individual basis, accumulated over time. When modeled against all known gravitational forces, a residual pull remained, a phantom hand guiding the craft ever so slightly off course, precisely as if an unobserved mass were present. Beyond gravitational tugs, there were sporadic, faint radio signals. Starting in the late 1990s, intermittent, ultra-low-frequency radio bursts were detected by arrays like the Very Large Array. While these signals were exceedingly weak and often attributed to atmospheric phenomena or distant astrophysical sources, their peculiar cadence and origin vector puzzled some researchers. Dr. Elena Petrova, a radio astronomer, noted in 2008 that the signal often correlated with predicted transits of Thorne's hypothetical body, a coincidence too striking to completely ignore. These phantom signals remained inconclusive but added to the growing intrigue. Despite these intriguing clues, direct observational confirmation proved elusive. Multiple attempts to spectroscopically identify the hypothesized moon failed. Dedicated sky surveys, employing various wavelengths from infrared to ultraviolet, yielded no clear signature. This consistent lack of direct visual or spectral evidence fueled skepticism within the broader scientific community. Critics argued that the gravitational anomalies could be explained by complex interactions within the asteroid belt, and the radio signals by natural cosmic noise. Extraordinary claims require extraordinary evidence, declared Dr. Julian Vance, a prominent planetary scientist, reflecting the prevailing sentiment. In response to the mounting, yet unconfirmed, evidence, and Thorne's persistent advocacy, an international collaboration was formed in 2017, Project Luna Obscura. Funded by a consortium of space agencies, its sole mandate was to conduct a dedicated, multifaceted search for this potential hidden moon. The project brought together experts in orbital mechanics, radio astronomy, and advanced imaging, pooling resources and developing novel detection algorithms. This specialized initiative represented a significant shift from sporadic observations to a targeted, systematic hunt for the elusive celestial body. Project Luna Obscura faced immense challenges. The faintness of the object, coupled with its highly erratic and distant orbit, made precise localization extraordinarily difficult. Teams employed a network of ground-based observatories and space-based sensors, attempting to triangulate its position. However, as noted by lead orbital analyst Dr. Kenji Miyazaki, the angular resolution required to pinpoint something so small and dark, moving against a field of countless stars, pushed our technology to its absolute limit. The margin of error was vast, often leading to weeks of fruitless observation based on initial, imprecise calculations. A critical piece of the puzzle was understanding why the object was so dim. Early hypotheses, according to Dr. Thorne's team, suggested a composition akin to carbonaceous chondrites, the darkest known meteorites. This albedo paradox indicated a surface that absorbed nearly 95% of incident sunlight. Further spectral models, later corroborated by preliminary data, indicated a thin, volatile ice layer sublimating under solar radiation, combined with significant deposits of carbon compounds and possibly ancient, ultradark silicate rocks. This unique surface composition was the primary reason it had evaded detection for so long. Even without direct visual confirmation, Project Luna Obscura's orbital dynamicists worked tirelessly to refine the predicted path of the hidden body. Utilizing the accumulated gravitational perturbation data, sophisticated n-body simulations were run, charting billions of potential trajectories. Dr. Miyazaki's team eventually converged on a highly elliptical, retrograde orbit, with a period estimated at approximately 27.5 days. This unusual path, significantly different from our primary moon, explained its infrequent visibility windows and the complex gravitational interactions observed in the stereo spacecraft data. The nature of its origin immediately became a subject of intense debate. Two primary theories emerged: the accretion theory and the capture theory. The accretion theory, favored by some planetary geologists, posited that the Moon formed in situ from the same protoplanetary disk as Earth, but perhaps under unusual conditions leading to its dark composition. Conversely, the capture theory, supported by orbital dynamicists like Dr. Thorne, suggested it was a rogue asteroid or dwarf planet captured by Earth's gravity much later in the solar system's history, explaining its eccentric and inclined orbit. Both had valid arguments, but lacked definitive proof. The pivotal moment arrived in late 2021. Leveraging the newly upgraded James Webb Space Telescope, JWST, and an innovative long-exposure stacking technique, Project Luna Obscura finally achieved direct visual evidence. A series of faint, pixelated images, taken over 72 hours, revealed a minuscule, shadowy disk against the backdrop of distant stars. Though blurry and requiring extensive digital enhancement, the images matched the predicted trajectory and apparent size with astonishing precision. This was the first time humanity had seen this elusive celestial companion, marking a monumental breakthrough. Following the JWST's initial images, an immediate validation effort was launched. Dr. Thorne's team, in collaboration with Dr. Miyazaki's Orbital Dynamics Group, overlaid the visual data with their most refined trajectory models. The alignment was nearly perfect. In a joint press conference, the Thorne-Miyazaki confirmation was announced, definitively proclaiming the existence of Earth's second moon. This moment, broadcast globally, reshaped our understanding of our own planetary system, turning a theoretical anomaly into a tangible reality. The years of doubt and rigorous pursuit had finally culminated in undeniable proof. With confirmed sightings, more precise measurements became possible. Analysis of its angular size and gravitational effects yielded an estimated diameter of approximately 200 kilometers. Its mass, while significantly smaller than our primary moon, was calculated to be substantial enough to exert observable gravitational influence. These initial figures, reported in Nature Astronomy, placed it firmly within the classification of a minor moon or a large, captured asteroid, rather than just space debris. This critical data allowed for the refinement of all previous orbital models and compositional hypotheses. Further spectral analysis, now with direct imaging to guide observations, confirmed the initial theories regarding its dark composition. The data indicated a surface rich in carbonaceous materials, similar to D-type asteroids, along with traces of water ice and complex organic molecules. This suggests a pristine, relatively unaltered body, likely originating from the outer solar system. Its surface is essentially a time capsule, remarked Dr. Ilara Vance, a planetary geologist, offering clues about the early solar system's chemical composition and the potential delivery mechanisms of volatiles to the inner planets. The discovery also prompted a re-evaluation of our existing moon's orbital dynamics. While subtle, the gravitational influence of the newly discovered moon, provisionally designated Luna Secunda by Project Luna Obscura, has been shown to contribute to slight, long-term perturbations in Earth's primary moon. Dr. Thorne described this as an echo effect, a faint but persistent resonance. Researchers are now meticulously modeling these complex three-body interactions to fully understand the long-term stability of Earth's entire lunar system and predict any future minute shifts. The existence of Luna Secunda has necessitated a revision of celestial mechanics textbooks and planetary models. Our solar system, once thought to contain only one natural satellite for Earth, now reveals a more intricate picture. The discovery underscores the dynamic and often hidden nature of cosmic environments. According to a recent editorial in Science magazine, this challenges our assumptions, reminding us that even in our immediate cosmic backyard, fundamental discoveries still await. It pushes scientists to reconsider the parameters for what constitutes a stable, long-term capture orbit. The confirmation of Luna Secunda immediately sparked discussions about future exploratory missions. Its primitive composition and potentially unaltered surface make it a prime target for robotic probes. Scientists hope to retrieve samples to directly analyze its carbonaceous material and search for evidence of the organic molecules hinted at by spectral data. A conceptual mission, tentatively named Obscura Lander, is already in preliminary design phases. Direct study of Luna Secunda could offer unprecedented insights into the origins of water and life in our solar system, stated mission architect Dr. Liam Chen. While designated Luna Secunda, its official classification as a moon remains a subject of ongoing debate. Some planetary scientists argue its small size and likely captured origin makes it more akin to a quasi-satellite or a large asteroid in a temporary orbit. Others, citing its consistent long-term orbital stability, contend it meets the criteria for a natural satellite. As Dr. Leena Sharma from the International Astronomical Union noted, the terminology needs to evolve with our discoveries. Is it a moon, or a captured asteroid that simply chose a very stable home? This dialogue highlights the evolving nature of scientific definitions. The discovery of Luna Secunda is more than just adding another dot to our celestial map. It's a testament to the persistent curiosity of science and the power of technological advancement. It reminds us that even in the most familiar corners of the universe, mysteries can lie hidden in plain sight, waiting for the right tools and minds to uncover them. This quiet revelation expands our cosmic perspective, prompting us to look deeper, challenge assumptions, and acknowledge that the universe, even our immediate neighborhood, holds wonders we are only just beginning to comprehend.